Hello and welcome to our Lunch and Learn session about ArangoML. You might wonder, what is actually ArangoML all about? What we are seeing currently in the overall ML space is a growing importance of graph technology. So for example, if we're just looking at big companies like Uber, Twitter, or even Google, who, for example, used graph machine learning to improve the prediction rates of Google Maps, which many of us probably use. On the other hand, also on the scientific front. So first of all, if we just look at ML conferences like NeurIPS and others, an increasing number of tracks is concerned with graph technologies or graph influenced machine learning. And also many of the breakthroughs, for example, for antibiotics, for drug resistant diseases and others are actually powered by graph technology or graph machine learning in the background. And this is what actually this talk is about. We'll talk a little bit about ArangoML, and we'll cover two aspects of this in this talk. The first one is graph-powered machine learning. So we'll dive a little bit into graph analytics, talking about feature and model engineering here, and then also discuss like basically what are other machine learning related technologies out here you can leverage on graphs. The second kind of orthogonal aspect is a bit more concerned with the ML operations side of things, but it's basically how can you leverage graph databases or databases in general to track metadata across your pipeline, for example, for GDPR or CCPA purposes. So I'm Jörg, I'm the head of engineering and machine learning at ArangoDB. Basically, my entire career, I've been working on databases, starting from my PhD, worked over at SAP. And then also, second aspect is building large-scale data and machine learning infrastructure, both in finance and healthcare. So I'm really happy I can combine all of that, those passions into one role, and actually also right now here into one talk. So the first question is, what is actually GraphML? So just to take like a little example, we can start out very simple. So if we start out with a simple graph tree, which is more like in the realm of a generic graph database, would be who can introduce me to X. So if we're looking at a graph of people, that could be your favorite social network graph, Facebook, LinkedIn, etc. It's basically like trying to find a path between two nodes, between two peoples. The second, a bit more challenging task is in probably graph analytics. And this is actually when we want to gain knowledge from the overall graph structures. For example, who is the most connected persons, where actually the disjoint subcommunities, and questions like that. The last and probably then most advanced technique is actually when we bring in machine learning into the picture and actually train a model and then try to leverage a model. And such model could, for example, suggest new potential connections. You all have probably seen that on Facebook, Twitter, where you get all those recommendations like, hey, you might actually want to connect to X, you might want to connect to Y. But it also has applications in other fields. So for example, you can also try to predict node labels. Imagine, for example, someone likely to churn. And here we can already see that just the graph aspect can be rather helpful here because we can actually take into account the neighborhood. Imagine all your friends have just left your favorite social network. What does it actually mean for you? You're probably also more likely to actually churn away. And what other problems can we solve? So with graph analytics, we can do things like community detection, recommendations, centrality. This is exactly the question we had earlier, like who's the most connected person, who are the influences in a graph. We can do path finding, and this can be leveraged for fraud detection, permission management, and a lot of other things. Then if we actually go over to GraphML, it's actually about learning graphs. So node and link classification, link prediction, or overall classification of graphs, where this can be helpful. To just take like a concrete graph example and then see what we can, how we can apply those techniques here, let's actually take a rather well or famous data set in the graph space is the Cora citation network. It's basically a number of scientific papers and then who is citing those papers plus a bit of meta information. So for example, the class labels and also content IDs with additional meta information. A simple graph query would just be who cited this paper. So basically trying to find that direct neighborhood. Very simple query, but still can give us like rather interesting outcomes. The next kind of question we could ask is like more in the graph algorithms, graph analytics space. What are the most cited papers? What are actually subcommunities who are always citing their own papers? If you ever worked in research, it's, I mean, on the one hand, it's pretty natural to just see like that certain fields are probably going to be more citing in those fields, like a biology paper is less likely to cite a computer science paper, but often it's actually also driven by for example, like colleges, by universities, more citing papers within their own network. So this can actually be helpful to identify those sub-networks citing each other. And then if we actually have built a machine learning model, we can leverage it for tasks like predicting reviewers, predicting or adding missing citations, which might have been lost because we're only citing within our network, or we can also predict other node features, so for example, paper labels or other things. You might wonder what's actually different between traditional ML or graph ML. So why is like graph ML becoming this new important role? And this is actually because we can take the neighborhood more into account. Like a very common assumption in ML, it's not everywhere, but it's rather common, is that each data point is kind of like independent, identically distributed. And so if we would take a look at this network of people, it would actually mean we would just treat each data point with its own features more or less independently. If we actually look at that in a graph context, we actually often see that as well in real world data sets, that this is actually not the case. We're really dependent on our neighborhood. And so there are some common assumptions for graph. And one might be homophilia, that neighbors are actually very similar. So you're probably in your social networks, you're connected to people who have similar ideas, who fall into a similar field. So it's actually a very valid assumption in many real world data sets. Another assumption is that we actually have structurally equivalent nodes. So often we have like central figures. So for example, imagine we are drawing a graph for like governments. We would end up having like very similar graphs. There's like some head of state, however that function is exactly called, and then basically branching out underneath a group of more and more politicians. And the structure of those graphs, even though it's not exactly the same, probably is very similar between different countries, between different graphs in that case. And for some graphs, we actually even have the opposite from the first assumption. So basically the opposite of homophilia would be heterophilia. And that would be that neighbors are inherently different. And this is often the case, for example, for bipartite graphs. So from there, we would actually assume, because we have a certain label, that our neighbors are less likely to have the same label. So with that, we're actually seeing this growing importance of graph analytics and ML. We actually, if you want to dive into more detail, would just recommend like checking out this page. We have a number of use cases. We have a number of tutorials, which unfortunately in this lunch and learn session, we don't have time to go through all of them. But in the end, I actually also link to a workshop we have done on graph analytics, where you can actually play with a lot of interactive notebooks to get started on that. So if we look at GraphML, we mostly right now talked about like simple graph analytics use case, trying to find subcommunities, trying to identify influential persons. But what can we actually do to take this next step, as mentioned, to like really having a model in terms of a machine learning model? And the challenge here is that machine learning models, what they usually deal with very well is some kind of tensor, some kind of matrix vector input, but not very well with something unstructured as a graph. And so there are multiple techniques to deal with that. And the first one is actually about embeddings. So embedding is basically about how can we map things to a vector, to a tensor, and then leverage from there. And the usually easy example, and this is where embedding, a lot of the embedding research is actually also coming from, are word embeddings. So words basically have the same challenge. How can we embed them into a graph? How can we embed them into a vector, into a tensor? And so here, we could just map it to a random number, to a random vector, but we would lose a lot of information. So if we actually have between words, we have certain relationships. So for example, Spain is the capital of Madrid, Italy is the capital of Rome. So if we map that into some kind of 2D, 3D space, we would actually assume that the difference between, or the vector in between Spain and Madrid would somehow be similar to the vector between Italy and Rome. And for example, also we would assume that walking is closer to walk than, for example, to swimming or swam, because it's actually the same verb in different tenses. So if we look at that, what that actually means in terms of graph, here's also, for example, already a notebook link. You can actually go through this example. And this is the Karate Club example. This is another rather famous graph example in graph research, and also like a lot of tutorials cover that. This has basically been a Karate Club, I believe, in the 90s, which split apart. So there was kind of like the trainer had a disagreement with the main administrator, so they actually split that club into two. And we have data about like how the members interacted with each other before. So this is basically what you can see here on the left. All those lines denote some kind of social interaction outside of the club. And with this kind of social interaction information, there's graph is used as a data set to basically predict, will those members end up in the new club of the administrator, or will they end up in the new club of the trainer? And so if we apply graph embeddings, this basically means for each of those nodes, we map it to a two-dimensional space here, and then draw that, graph it here. And if we actually look at that, just from turning this graph into a 2D embedding by taking the social interactions into account, we can actually get a nice linearly separable data set between those two clubs. So the different colors basically represent the clubs in which they ended up in the end. And as you can see, we can actually, just by taking an embedding into a space there, we can then apply like very simple machine learning techniques such as support vector machines or others in that 2D or also often more high dimensional space, to then deal with that graph data and basically predict, are they going to end up in club A or are they going to end up in club B? As mentioned, if you really want to run through this example front to end, I really recommend this interactive notebook. Nothing to install, just run it on Colab here. If those embeddings are actually not sufficient, we can take it like a step further, and that would be towards graph neural networks. And what graph neural networks do, they basically create a new representation of that graph from where we can then do node classification, entire graph classification, or also link prediction overall. So we could also apply graph neural networks to the same problem we've seen before, which would basically be node classification, trying to predict in which of the classes they end up in. And by doing that, it's computationally more expensive often, but we can also take other node features into account, whereas we can then also get better results. So this was kind of the first part, basically an overview of what we can do in terms of graph analytics and graph ML. So now just basically to the second part. And this is then more aimed towards like the MLOps side. So basically people who are now implementing such technique in a production pipeline. And if we are building a production machine learning pipeline, it often ends up looking like this. We have some data on the left, we do some feature engineering, model training, model management, and then model serving very much on the right side where we actually leverage and get some outcome out of that. So the challenges here, and this is, for example, for me, this was one of the examples I faced in my past, that we wanted to be able to identify, like, here we had some patient records on the very left in our data set. And now once this doctor actually tells us like, oh, you cannot use my data anymore, we just wanted to be able to identify like, hey, which models are actually impacted by that. And it took us like half a day going through like this entire pipeline to understand the provenance and identify like all the models being impacted here by this one data set. So there we actually identified, oh, we are missing some like global information about it, which would make such tasks and many others much, much simpler. And this is where we decided to actually build a common metadata layer. And this is now also being taken up by a lot of other projects. So for example, TensorFlow or Kubeflow also added a common metadata store, which by the way, we also integrate with ArangoML. What is metadata in this sense? So metadata in this sense, I've just taken here the definition from Kubeflow. It's like information about the runs models itself, other than just the core data. So other than the core model, it basically, it would be a model description. Where is this model stored? Which version is this model? And similar with a data set. So basically everything describing the data itself. And when I then joined ArangoDB, we actually built an open source project called ArangoML pipeline, which is a common extensible metadata layer for ML pipelines. So it makes it really easy to plug into like generic ML pipelines because it's based on the graph structure. So it doesn't prescribe like a certain set of rules. And it, for example, also integrates with TensorFlow and other systems out of the box. And with that, if we actually had that, it just becomes a simple graph reachability query. So we have a data set, and now the question is like, which models can I reach in this graph from this data set? So it becomes a very easy query to answer that, because we can naturally think about it as a graph problem and not, for example, as a relational database problem where we have to merge and where we have to join and self-join a large number of different tables. So it also comes with a UI, for example, for discovering data sets, for discovering metadata. And of course, it also comes with a graph representation where you can see what's actually all flowing into like an experiment, into a deployment, what is related to that. So that's our short lunch and learn session. I really wanted to keep it down to a lunch level, but we have a lot more materials. So as mentioned, we got a lot of tutorials going in that direction, both for the graph analytics and graph ML side of things. I actually have a talk coming up end of May at Data AI Summit, which is covering graph-powered machine learning. And we also have an O'Reilly workshop. This is a bit longer, but it actually gives hands-on experience on those topics. So if you're interested in that, I would highly recommend to go into that direction. Thanks a lot for listening. Feel free to provide feedback. Just reach out via Twitter, LinkedIn, or your favorite medium. Thanks a lot.